Good morning, ladies and gentlemen. The technology I'm going to refer to is a component of mine automation technology here on Earth, and I guess I'd make the point then, well, you know, if you're going to go off Earth, then some of this technology, some of this capability may also be relevant under those circumstances. So if we look at sort of the terrain that we could claim is familiar, that's of course sort of an example of Australian terrain that the mining industry operates in. And in the bottom right we have here something that is alien. It's an image from Mars. So when you look at those two, one thing, the structure of course is, well, one doesn't have blue sky, but apart from that, you would imagine that the challenges of at least navigating your way, positioning yourself relative to objects or relative to a reference frame may be similar. And that's certainly, of course, in the context of mining, but it may relate also, of course, to many other activities, both on Earth and off Earth. And again, I'll be coming back to this thing, to this issue that, you know, there are some things off Earth that we currently do or will be doing here on Earth, but of course there's always the important link component that actually gets this technology, adapts the technology, and even delivers it to where you want the activity to be transferred. So here's a hole. I don't suggest that perhaps this is the sort of magnitude of hole that will be dug on an asteroid, but it's the type of state-of-the-art open cut, open pit mining that we currently use. And it's all about digging a hole in this context. I can't imagine that off-Earth mining is going to be tunneling based, although I could be wrong. It's more likely to just be scraping the bottom, scraping the surface, scraping in an area after you've gone through the prospecting of determining exactly where you do want to focus your activity. And here on Earth, we have people such as these wearing fluoro jackets, hard hats, and using technologies which are linked to machines in a way that perhaps is not entirely obvious to the man in the street. And the machines may range from the sort of Lego stylized machines that are sort of mimic what we currently have on Earth, but obviously would, as Gordon has said, we cannot expect them to just be sort of picked up, put into a rocket, and then sort of landed on another celestial body. But let's look at this mine automation from both the humans and the machines. Although, of course, obviously what we're going to be doing is removing the human, just as we are removing the human from on-Earth mining. So I'll start from two perspectives. One is two geospatial perspectives, let me say. One is surveying and mapping of the mine site. Could be related to prospecting, so it's mapping of some form. Could be by remote sensing, could be by near sensing. Before, during and after mining or after such activities. There's the other part of the activity which is relating to the positioning of the mine equipment, because you really need to navigate, you need to track, you need to guide these machines, particularly if there's more than one of them, and also when you actually want them to go in a certain direction and mine in a certain way. Certainly on Earth, that is extremely important. It may be less so if what you're actually going to be doing is nibbling away at a big rock. But again, you probably want to do it in such a way that you're not going to cause problems for yourself, or not yourself, but problems for the mine activity. So let's keep in mind those two activities, two geospatial activities related to on-Earth mining, and see how they are evolving here on Earth, and perhaps how that could be an analogue for the off-Earth activity as well. Well, this is the traditional way you do it. We have humans standing around tripods with various types of equipment, tripods and poles. On the left-hand side, we see the more traditional total stations, which can measure distances and angles, and these days also probably laser few other things. On the right-hand side is the GPS clones, or GNSS technologies, which are coordinate devices. The left-hand side, they measure geometric quantities from which coordinates derive. The right-hand side, you directly derive coordinates from signals transmitted by satellites. Okay. So today's product is more than just points and objects, straight lines and such things. They may be quite complex plans, proposals for where the mining activity will occur. In this case, it's actually underground activity, underground mining activity, upon which sort of the surface terrain or surface images are superimposed. And of course, they can be much, much more complex. This is entirely digital, so we really are dealing with three-dimensional mapping, three-dimensional navigation. And really, the physical world is just, in a sense, in the way of these models. These models may drive where you want to go, where your mining equipment will operate, or what you want to be remain after the mining operations. Or it might be close to reality, and that is what this mine currently looks like. So you've got this virtual world and the physical world being mapped, and being mapped continuously with ever more sophisticated technologies. And what we're seeing here with on-Earth mining is that humans are not very productive, and of course they're also getting in the way. And certainly safety is one of the major drivers for moving from mine sites. But if we look at it from the perspective of the human as an observer who makes measurements, who then creates the geospatial information, the maps, then we have other technologies which are really with digital cameras, with laser scanners, with radar, and various other sensor technologies, which are used both here on Earth and also when we have spacecraft going to the Moon, Mars, asteroids, and so on. Essentially, the technology, the sensing technology is very simple. Optical, maybe radar, it may be gravity sensing, it may be magnetic sensing, and so on. But essentially, you're using a platform, a sensor platform, that from a distance is able to cover really, really wide areas. And unmanned or unmanned aerial vehicles, there's acronyms now associated with these, but basically they're the new workhorses. They're the workhorses here on Earth, and well, how useful would they be in off-Earth environments? So certainly from the perspective of photogrammetry, that is taking digital images with cameras, and increasingly also carrying aloft laser scanners, they are certainly revolutionising rapid mapping. Now, the problem with UAVs or off-Earth mapping, or off-Earth mapping application is that you need propulsion systems, certainly increased automation and autonomy. You need ground control points if you're doing photogrammetry. LiDAR requires direct georeferencing, so we need positioning and attitude determination to derive externally in some way. And today, GPS and GLONASS, collectively called GNSS, Global Navigation Satellite Systems, are the tools of choice. They are making it possible to experience this revolution. So where are we with off-Earth analogues of GPS? Okay, let's look at the mine operations, the machinery operations. The traditional way is for machines that work in close proximity, guided by planning, guided by stakes in the ground, guided by perhaps humans, guided by other means to ensure that the drivers of these machines are mining according to some plan. And there may be some technology assistance, but essentially the traditional way was to have humans, to have miners. The progress has been, of course, in the direction of automation of those machines. They may just be remotely controlled. and the degree of remoteness could vary from just a couple of meters, a couple of 100 meters, a couple of kilometers, to perhaps thousands of kilometers. But artificial intelligence, not something that you would probably find in many mine sites today. Miners are extremely conservative, and I suspect they would like to have somebody controlling a joystick, no matter how far away it is. But clearly the direction is to greater autonomy, for example, for vehicles in the mine to have no drivers, even though they may still be overseen by a control centre. And that means that you can pack the vehicles closer together without the danger that maybe the vehicle will run into another vehicle or into something so small that is not noticed up where the driver sits in normal circumstances. Well, machine automation, if we look at the mines, we say, yeah, that's happening. Of course, it's going to happen. It'll happen at the pace at which they have to renovate the mines and plan it. And it'll take many, many years and millions and millions and millions of dollars. On the other hand, driverless cars are increasingly finding their way onto the roads. They're even getting, in certain states in the US, getting licenses to be driven. I'm not sure if they have to have a passenger. I can't imagine that a driverless car without a passenger makes a lot of sense and be allowed on the road. That begs the question, as people say, well, driverless cars will be better cars because they're smarter, they don't fall asleep, they don't text at the same time as driving. And it means that they can pack more closer together. So if you have a passenger in a driverless car, the traffic jams, everything will be squeezed in, right? So it's 2 lanes of traffic being in close proximity. You'll have 3 lanes of traffic because these driverless cars really can position themselves in ways to some estimate accuracy. And if you think it's only 1 or 2 cars, think again, this is a fleet Google cars with these strange pods coming up. They're still experimental. They are the eyes, the ears, and the full sensor suite of lasers and radar that will allow for automation. But essentially these things are collision avoidance systems coupled with a navigation component of the GPS, which of course is really driverless cars are just another form of robot, even though if we insist that we have to have a passenger in a driverless car. It's only, I guess, just to sort of make other road users at ease with vehicles that appear to have a significant amount of autonomous control. So if we look at the robotics, obviously we're going to hear a lot more about the Martian experience of robotics that has to have a significant amount of autonomy, has to be able to sense its environment, it has to see, it has to feel, and then decide how to get from A to B. It may not know what coordinate it's at, or it might create its own internal coordinate system, because on Mars there are no signals of GPS satellites. So, navigation without GPS. Well, vision and LiDAR, or laser-based navigation systems, work really, really well. As I said, they are critical to driverless vehicles, and if you add SLAM, simultaneous location and localization and mapping, it's also a pretty dirty way of mapping the environment, so that if you come back to it, you can sort of be familiar. Oh, I've driven this way before. Let me pull it out of my database. And, okay, so you want me to dig here? Okay, I've been here before. I know what's around here and so on. But it's still inherently, shall we say, in a box type approach to positioning and mapping, because it implies that you have to sort of like mow the grass almost, going backwards and forwards to work out where you are and what's in the area. And then you're very much like medieval sailors and navigators, you're at the edge of the world where if you go too close to it, will fall off. And that's really where the way autonomous robots will typically work. They'll mow an area, they'll know it very well, and it's sort of like a boundary that you don't go beyond that sea surface, and so on, which is something that we've grown out of, that sort of view of the world. So what are the off-Earth positioning technologies? Well, why don't you just transplant GPS? And it's have a constellation of satellites broadcasting signal around a celestial body. One would expect a celestial body to be a lot larger than an asteroid. Because when you think about how many satellites you have to deploy to get coverage, global coverage, 24 hours. I'm not sure you can say 24 hours a day on an asteroid, but you know what I mean. Continuous coverage. Where would they be launched from? It's already pretty hard to keep GPS constellation alive, believe it or not. It doesn't just consist of satellites. There's hundreds of millions of dollars a year invested by the government and lots and lots of people on the ground who actually monitor the clocks and make sure that everything is okay, ultimately make decisions about the deployment and redeployment of the GPS satellites, which normally they're 24, but actually there are 32. But mining is a localized activity, so it seems to me that you're trying to crack a nut with a sledgehammer if you think that, oh, I'll do mining on a patch of the moon, all I'll need is 24 satellites in orbit about the moon, or thereabouts, pretty few, and solve all my problems about geopositioning. Well, again, we come back to the on-Earth model. That is, well, you can use GPS on Earth because GPS is here, but why would you develop an alternative or a backup or an augmentation to GPS here on Earth? And whether that, and if you could you then use that instead of an expensive and complex space, or satellite basis, to do your geopositioning anywhere you want to go? Because remember, you're doing this on a localized context. 1999, there's the paper Mars Exploration using self-calibrated pseudolite arrays. That, again, this is, you can see clearly the notion of you're covering an area which could be several kilometres across. There has to be line of sight. You have a mobile object being positioned in relation to ground transmitters, which are similar to, of course, the GPS satellites, except that the GPS satellites are 20,000 kilometres or more away from the user. So this is a local positioning solution. And it certainly spawned a few PhD topics. Stanford University then led to commercialisation efforts by several of the students. They formed a company called Integranautics. We purchased a couple of their pseudolites here at the university. It then became a company called Novariant, which tried to address the autonomous agriculture market. It since has been purchased by Trimble a year ago, but we don't know where it currently is. So Locata is really just a graduation from that concept of terrestrial transmitters, which combined with the GPS signals give you that full coverage. And it's really since post-2011 that this development has gone sort of commercial for the mining market, the open cut mining market. And it's pretty clear why you want it for the open cut mine market. Well, basically because the number of satellites that you can see across a 24-hour period drops alarmingly as you get deeper and deeper in the hole. So the sky view can be reduced. So if you're operating near the walls, you don't see as many satellites. So on Earth, Locata was seen as an augmentation, that is extra signals that can be transmitted that you could then use when GPS was not available. Or when both are available, you can combine in the classic multi-sensor integration context. But if you take GPS away, Locata can still operate. And for example, this is how it would be on a mine site, powered by a solar array, small patch transmitting antennas. Here's an example here, UNSW, and here's an example for an indoor demonstration. So it's hotspot deployment, and it certainly is in satellite. So this idea of hotspot, you can do navigation in the context of true coordinate-based navigation as opposed to collision avoidance type navigation. You can do it with the deployment of hotspot signals specifically designed for measuring distance very, very precisely. Newmont mining the gold mine for several years. They've been operating this technology and comparing it side by side with GPS. As I said, the mining industry is very conservative. You really have to get in their face for a long, long time before you get them to change habits, even if these habits were GPS, which itself probably took many, many years to get into the mines. Several years alongside objects. For accuracy, we're talking here about similar accuracies to GPS. So this is not Wi-Fi type positioning. It's not thereabouts type navigation. It's not sort of inertial type navigation. This is serious coordinate-based navigation where you really want very precise positioning. The product is known as JPS. So it was actually launched last year, September 2012. So this box actually exists. So when there's no GPS, which means no until it doesn't work, it will still be able to do positioning. So we're not talking here about, a PhD topic. We're not talking about something that was an idea that could be commercialised if you gave me, $50 million. It actually works right now and is being deployed in open cut mines in Australia. This is an example of this productivity improvement that shows that it does work when GPS doesn't, because in this case here, only 41% availability of the number of satellite signals in that mine would have meant that this mine automation would not have been able to go ahead if it did not have the ability to get coordinates from another source. So I'll just scroll up the concluding remarks, and I guess what I'm just, that's the takeaway message. You want to deploy something like this on the ground now, covering an area of several kilometres, or even, as in the case of the White Sands missile range, several thousand square kilometres, where they're boosting the power up, of course. You have a technology which actually can work without GPS signals, which means that it can be taken somewhere where those signals don't exist. Obviously, it can't be used underwater, because we're still dealing with RF signals. But, that's not the challenge that we're going to be facing with off-Earth navigation, off-Earth object navigation. Thank you very much.
How have you managed time-based stability in the Locata base stations when you don't have the local reference that is the GPS system to give you absolute timing accuracy?
For navigation, you don't need absolute timing, you need relative timing. So one of the master locator transmitters drives the synchronization of all the others, because essentially you're still solving for a receiver clock as you would with a GPS receiver. And GPS time, which is what you were referring to with the synchronization from GPS, that in effect is synchronized from the ground anyway, but the atomic clocks are then operating autonomously, whereas in the locator concept, everything is slaved off one clock.
Okay, the other bit of the PNT question. As you just said, it doesn't need to be synchronized with timing, but each of the locator transmitters need to know where they are. So,
yes.
How would you go about surveying them in the first place?
Good point. You can do self-survey by basically adopting a position for the master. That would in effect define the reference frame for that local area. In fact, the moon's surface is better mapped than the surface of the Earth. So in fact, you could zoom into any point on the surface of the moon and probably have sub-meter accuracy if you can find that piece of rock or whatever. But in a sense, that's not needed, because if that establishes its reference frame, just like a GPS network on the ground establishes a high precision reference frame, because the satellites don't provide the meter level positioning accuracy on their own. So you do need to have that ground component. Here you have everything on the ground. And you can connect a clock to it if you want to set up a particular time system. So it's a means also of distributing time to the rover. So forms both P and T.
Any other questions? Thank you again, Chris.